In this video, we will cover the 5 ways to determine the order of reaction. All right, so if you still remember, how do we define the order of reaction? So order of reaction is defined as the power to which a concentration is raised in the rate equation. All right, so maybe I should do a little bit annotation here for you to recall. All right, or maybe you can just look at where am I highlighting now? This is the power. Okay, can you see the yellow highlighter? The power to which a concentration is raised in your rate equation is called the order of reaction. And today we want to know how do we calculate or determine the order. There are total 5 ways. Number one, I give you the 5 ways first. Number one, we want to look at the graph of concentration against time. So you just need to look at the line, okay? So whether the line is a straight line or curved line, okay? Second, we look at the graph of rate against concentration. Same thing, you just want to look at the line, whether is it straight, curve, or horizontal, or diagonally upward, then you know what is the order, all right? Number 3, we're going to use successive half-life. Number 4, involve normally a table. And number 5, rate determining steps. So we'll go through all this 5. Now, let's look at the first method first. Okay, now the first method is you need to look at your graph against concentration against time. So now when we take a particular reaction, reactant will decrease over time. So you can look at the diagram over here. There is a black line in a decreasing manner, but it's a straight line. We call this a zero order. That means your power to 0. Then you have a curved line, which is orange in color. This is the first order. Your reactant also decreases over time. Second order, you can see the line is more curvy because it decreases faster. Okay, so all the lines are in decreasing form because reactant decreases over time. So it's concentration against time graph. Now, so when you get an experiment, normally we will look at how concentration changes over time. So we will normally look at reactant. Of course, your question can come out the formation of product, how fast the product is being formed over time. Okay, but that one, normally we don't look, but sometimes they come out. But we're going to focus on reactant decreasing. All right. Now, so it's very simple. You just need to look at the pattern of the line. Okay, so therefore you know what is the order. Now I'm just going to take one partial question, which is a summer 23 on the right hand side on the screen. They give a particular equation called iodate and 6 proton and 5 iodide to give 3 iodine and 3 H2O here. So the question give the rate equation as such. Now what does it mean? It means that with respect to the IO3 minus the iodate ions, okay, you can see it is to the power of 1. To the power of 1 means it is first order with respect to iodate. Okay, now over here, your H plus is power to 2. That means it is second order with respect to the proton ions. Remember, we do not raise to the number of moles like Kc, Kp. Iodide also second order, specifically for the iodide. Now, if I want to sketch a line, okay, individually for the 3 reactant that's being involved, okay, so maybe let's look at how we can do this. So we're going to draw a concentration, okay, versus time in seconds, okay, or time seconds here. Now, knowing that IO3 minus is power to 1, hence the line will be curved. Okay, so this is for iodate. We can see that iodate decreases because it's a first order power to 1, hence you draw a curved line. Now for proton, okay, H plus, it's second order, so you may want to draw a more curvy line, okay, which is H plus, a more curvy version. Okay, now for information, you don't really have to start with the same starting point, which is over here. Okay, but so long the curve is more curvy. Okay, now let's take another example. Iodide ions is also second order given in the rate equation, right? So let's say I'm going to start with a very, very curvy line, but maybe down here, like even curvier. But I'm going to start at the lower concentration. So I'm going to make a very curvier line, and this is called the iodide. Okay, now we only can fathom qualitatively, it's not going to be accurate because how curvy a line can be is different every time we judge. Okay, now this is a very easy method to know whether it's a zero, first or second order, especially for the zero order, because straight line, everybody can see, we know it's a zero order, so therefore you power to zero, case close. But when you come out a curved line, okay, therefore the challenge comes in. How curvy does this line look to me? Whether should I call you a first order or a second order reaction? So that is the limitation of the first method. It's fast, but it has limitation because we can't differentiate the first and the second order. Okay, yeah. Now, so let's look at another question over here. All right. So they said that the rate of reaction between the 2-chloro-2-methylpropane and methanol is investigated. Large excess of methanol is used. So when you want to determine how 2-methyl-2-chloropropane affects the rate, we will normally make the other counterpart, which is methanol, excess. Okay, so therefore, when the concentration of the methanol is excess, whatever change in rate is solely contributed by the 2-chloro-2-methylpropane. Understand? All right. Now we can see that first they plot a graph for us conveniently to show how the halogen alkane decreases over time. And when I look at this line, I saw a curved line. Now, curved line means it can be first or it can be second order. All right. So are we going to judge whether is this very curvy to be second order? No, we're not going to do that. All right. So you can see that this curve line, we can't know whether is it a first or second order. But of course, later on, there's a way to differentiate first or second order. Okay, which I'm going to go through now. So because there's a limitation in method number one, therefore there is method number two on how to determine the order of reaction. Okay, now, so method number two over here, I will come back to that question again, is we want to look at the graph of rate against concentration. Okay, so let me show you method number two first. Method number two requires you to plot another graph, or perhaps maybe your examiner will print it for you. There are three types of line. The zero order line, which is a straight horizontal line, a diagonal upward lines indicating a first order, and a curved upward line indicating a second order reaction. Now, this is very nice because there is no confusion between the first or second order of reaction. All right. Yeah. So, but the downside about method number two, all right, is where you need to obtain the rate. So the question now is how to obtain rate. All right. Now, if you go to the lab to obtain raw data means the data that is read from a apparatus or a machine. Yes, you will read the concentration. Concentration is translated from the volume. For example, your average volume in your titration. So you can calculate to your concentration. Okay. So when you obtain data, right, obviously most of the time you will come out with a graph of concentration against time. Now you need to translate the first graph to the second graph, which is called rate against concentration. And how do we do that? I'm going to show you over here. Okay. You need to plot the first graph first, called concentration against time. And then I need you to go and plot tangent. Okay, so let's say we're going to plot tangent for every 25 seconds. So first, I'm going to plot an initial tangent here. This is at minute 0. We call this initial tangent. Okay, now then I'm going to plot a rate at minute 25. So I want you to look at minute 25 here. Okay, at this dot. Okay, then you draw a tangent which touches the curvature once. So this is rate at 25. Okay, now then we're going to do one at 50. Okay, like this, 50. Okay, so I'll just do another two more. One at 75. So you look at 75 on the line, and I want you to plot a tangent. Okay, like this. Perhaps I'm going to do this. And then the last one at minute 100. Okay, approximately here. So this is for 0, okay? And this is for, where is my 25? 0, okay, I think this is 25. and this is for 50, and this is 75, and this is 100. Now you can see as the reaction progress, the rate, also called the gradient, decreases. Of course, because the reactant concentration decreases over time. So when you have lesser concentration, your rate will decrease. Okay, so the rate will decrease over time. Now, I need you to go and calculate the gradient here. Okay, and then you go and tabulate. Okay, I need you to do a tabulate like this. Okay, so maybe this is your time. So at time 0, what is your rate, which is your gradient? At time 25, at time 50, at time 75, and at time 100. Okay, now what is the number here? Okay, which is your rate. So let's call it as A, B, C, D, and E. We speed up the whole procedure here. Now, once you tabulate this, okay, then only you can go and plot method number 2, which is the rate, okay, against your concentration. Correct or not? Yeah. So now I need you to go and draw tangent. All right, minimum 5 times. We need 5 cross to plot a best fit line. Okay, now, so there are 3 ways on how the line will come out according to method number 2. If it come out a straight horizontal line, congratulations, you are 0 order. If it comes out a, a straight diagonally upward line, straight line, so this is called the first order. If come out an upward line, your best fit line come out like that, is called second order. All right, so we can see the method number 2. You can clearly differentiate between 0, first, and second order with confidence. Okay, but the downside about method number 2 is where you may have to go and spend a lot of time to draw multiple tangent, gradient, and replot a new graph called rate against concentration. Okay, that is the correct procedure on how you should do it. Okay, so the question now is, do you think you have enough time, and do you think your examiner will make you plot 5 times gradient and replot a second graph called rate against concentration in your exam? I would say unlikely. Okay, unless they have given you the table, provided they give you the table, given the table here, given the table below, please plot a graph of rate against concentration. Okay, then it will speed up everything. All right, and then you just look at the line, then you know whether is it a 0 first or second order. Okay, so method number 1, easy. You look at the line for the concentration against time. But the downside about this method is when you come out a curve, you don't know whether is it a first or second order. And if you are caught in a curved line, you may have to go and plot the second graph, which is rate against concentration. Then based on the line pattern, you will know whether is it first, second, or 0 order reaction. Okay, now 0, first, or second order, it means that the concentration is power to 0, power to 1, or power to 2 with respect to that particular reactant. Okay, yeah. Now, method number 3. Okay, method number 3 here is to use successive half-life. Okay, now this one is more common in exam. Okay, now what is the chances of method number 1 coming out and a straight line come out and then the student close case at 0 order? Low. Then it's going to be a very easy question because I just look at the decreasing straight line, 0 order. Okay, that's it. End of question. 1 mark. What are the chances do you think this will come out? Unlikely. Can. Okay, but unlikely. So it makes more sense you create some challenge for the student, you come up with a curved line. But the curved line means the student may have to spend a lot of time plotting the second graph. All right, then they can come up with an answer. Okay, I mean, doable, but time consuming. But there's another way. Instead of plotting another graph called rate against concentration, we can do half-life method. All right, now half-life, okay, also known as the T half, like this. T half, okay, T half. Now, half-life definition is the time taken for the concentration of a limiting reactant to fall to half of its original value. We normally look at the concentration of the limiting reactant because just now you saw the question, right? When you want to find how A affects the rate, you make sure B is constant. And how do we make B constant? We make it in excess. all right, then whatever change in rate is entirely on A's fault. Okay, yeah. So we will do it on the limiting reactant concentration. We want to see how does A affects the rate. Okay, now we're going to use half-life technique, which is the third way that we can find the order. Now, there are total 3 types of line, and I need you to go back to the first method, which is concentration against time. So you can see I open up into 3 different graphs over here. So this is concentration on the y-axis, mole per liter. Liter means dm cube. It's the same thing. So concentration against time. So obviously the first one, straight line. Okay, the students see this line here. Okay, immediately it's method number 1. Close case, this is called zero order reaction. Immediately, the end. Okay, now when you come up with a curve, which is what we want to handle here. Okay, now I need you to do a half-life, which is to go and plot on the graph, okay, every time it decreases by 50% of the concentration, how long does it take? So for example, original concentration is 0.2. Half of 0.2 is 0.1. Okay, now then if you look at 0.1 and you look down here, it takes a total of 7 seconds to decrease the first 50%. Okay, so the first half-life, all right, from 0.2, halve it to 0.1. Okay, the first half-life is first 7 seconds. Okay, now I want you to do the second half-life. From 0.10, if you drop half, 0.05. Okay, so you take your ruler, okay, and you sketch and you look down here. This number is called 14. Okay, now common mistake is student will read the second half-life as 14. No, the second half-life is actually 14 minus 7, the second bubble here. Because this is the amount of time that is making 0.1 decrease by half to 0.05. If you write 14, right, it just means that from 0.2 to 0.05, it took a 14 seconds time. But because you only want to look when 0.1 drop down to 0.05, which is actually 14 minus 7. So that would be my second bubble. Normally, I will say bubble. Okay. So second bubble here, second half-life is also 7 seconds, as you can see, 7s. Now, you can continue to find a third one. I try to find 3 minimum. All right, 3, the best I can. 0.05, you drop down half to 0.025. Around here, you look, and you look on the x-axis, the number here is 21. So from 0.05 drop down to 0.025 is the third bubble here. 21 minus 14, the third half-life is also 7 seconds. So when your half-life is constant, okay, when successive, okay, successive with the word, continuation, when your successive half-life is constant, therefore it is first order with respect to that particular reactant, which is called A. So your A is first order. So what it means? It means that when you write your rate equation here, rate equals to K, A is your reactant, right? First order means you power to 1. Then case closed. Okay, so this will solve the problem on how curvy the line can be in method number 1. Okay, and instead of going through a very, very long method to go and do a method number 2, which is plot another new graph, this will be a faster way, right? You use the same graph for method number 1 and you do a half-life, but I need to see the constructions line. Okay, so when your half-life is constant, therefore it is first order. But of course, please do not expect such an idealistic 777 to come out. You probably get something like, 6.9, 6.8, 7, 7, 7, 7, 6.8, 6.9. You're going to do an average of the successive half-life, and you give me the average. So for example, if the average comes out to be 6.9, then you say it's approximately constant at the average half-life called 6.9. Hence, it's a first order reaction. Okay, so first, you already learned how to do construction line of half-life in the concentration against time graph. You just need to use method number 1, but I need you to do some construction line. It's a faster way, all right, to separate between first and second order. Okay, so in your Cambridge syllabus, only first order for half-life is in your syllabus. That's why you can see I only write in the middle, which is for first order reaction. I never bother to write anything on the left, which is zero order, and anything on the right for a second order reaction, okay, because it's not in your syllabus. But anyway, since you're looking at it, all right, I also want to elaborate a little bit more on zero and second order. Why? Because the past year question have come out before. All right. No, so I'm going to quickly go through, but first order normally will come out in your Cambridge question. Okay, now for zero order reaction, right, you can use method number 1 to close the case really because it's a straight decreasing line. All right, but just in case, if you want to go and do an additional insurance, all right, you want to be very, very sure that it's a 0-second order with respect to your reactant called A, you can do a half-life, okay, to do an extra step, can. So what we can see over here is we do the same thing, 0.2, okay, drop down to 0.1 here. If you look here, okay, it took around, let's say, 33 seconds. So the first bubble here is 33 seconds, the first half-life. Now from 0.1, you drop another 50%, you drop half, right? And you read over here. So let's say this number here is called 50 lah. And 50 minus 33, right? So the T first half-life is 33. Now the second half-life over here is 50 minus 33, which is 17 seconds. You realize the second half-life is shorter. The bubble is smaller now. And if you continue to do a third decrease, which is 0.025, and you look down here, right? So let's say this number is 60 lah. Okay, let's say this number here is 60. You will realize the bubble here is shorter because your third half-life is 60 minus 50, which is 10. So what you can see here is that 33, which is the first half-life, decreased significantly to 17 seconds and decreased another time, all right, to 10 seconds. So every time this reactant decreases by half, the time taken shortens. This is a characteristic of a zero-order reaction, all right? The reaction will become faster in terms of how they decrease, how fast they decrease. That is for a zero-order reaction. And if you look at the last one very quickly for a so-called very curvy line, a second-order reaction, right? So if I were to speed up the whole procedure, you will see here is around like, let's say 50 seconds. Then let's say I estimate here is 150. So let's say this is 100. First bubble is 50. Second bubble take 100 seconds. 150 minus 50 is 100 already. I do the calculation quickly. The third one here, let's say this is 340. 340 minus 100 is 240. So what you can see here is the first half-life is 50, second half-life is 100, the third half-life is 240. It's just an approximate gauge. I'm just trying to speed this thing up. So for a second order reaction, so-called a very curvy line, the successive half-life will increase. That means every time they try to decrease by half, it takes a longer time. Okay, but like I said, zero and second order, which is the left and on the right, is not in your syllabus, but then it's okay, you now know. Okay, now, so normally I would suggest that you know all three. Okay, and what is the technique that I use? Okay, to know or memorize the half-life and which half-life, what kind of half-life is what order. I will normally draw a bucket here. Okay, so we will always write from left to right, right? So if you realize, I draw downward, straight, and up because regardless whether you're left-hand or right-handed, right, we will always write from left to right. So when I draw the bucket, I also draw from left to right. Okay. Now, when I move, when time move, okay, going down, if your half-life is decreasing, this is called zero. If your half-life is moving parallel, that means it's the same, okay, same, constant, okay, the word actually should be constant. Constant is the keyword, not same. Keyword constant. This is called first order. And if your half-life increases, okay, this is called a second order reaction. So can you see the number 0, 1, 2 from left to right? Okay, so now I know that if my successive half-life decreases, it's a zero order. If my half-life is constant, it's first order. And if my half-life is increasing, it's a second order reaction. So this is what I use. All right. Yeah, so that we don't get confused. Okay, yeah. Now, so repeat one more time. First order is in your syllabus, but zero and second order, I think they come out 1 or 2 times maximum, I think it come out like, not mistaken, maybe they can just ask like, oh, the half-life increases. What order is this? Okay, then you know it's a second order reaction. Okay, but it has to be a significant increase, like from 50 jump to 100. Okay, then it's very significant increase in the half-life. Then yes, I know it's a second order reaction. So because sometimes you get data, things like, things like 6.8, no, then 6.9 seconds, and then 7 seconds. Now, some students may read these 3 half-life as an increasing half-life because the number increases. Okay, then if you read it in an increasing format, then you will close case to say that this is a second order reaction. I mean, like, makes sense because the number does increase. Okay, but then you must be smart enough to know that 6.8 to 6.9 and 7.0 is not a very significant increase. All right, so if it's not significant, right, I will say that it's approximately constant at 6.9, which is the mean half-life, and our close case as a first order is approximately around there, anyone. So I'm just going to close this as the first order reaction where the half-life is constant at 6.9. I'll take the average 6.9. Okay, now before I close method number 3, okay, method number 3, you can see it's not a super lengthy method to the point that you have to redraw another graph, which is method number 2. All right, and it's not too straightforward like method number 1. You give them a diagonally straight decreasing line and zero order where you don't even test anything. Okay, I think it's just a right amount of work needed by student to come up with the order of reaction. Just draw construction line and then you gauge whether is it constant or not. Okay, or maybe perhaps they want to ask decreasing or increasing the zero and the second order reaction. Okay, syllabus requires you to know the formula for the first order reaction. So everybody, I use red color pen. Formula. So the formula for a first order reaction, we have this thing called the half-life equals to your rate constant. This K is this K. Wait, the other way around. It's actually 0.693, also known as ln 2, okay, over your K, which is this K. Okay, it's the same thing. Half-life for a first order reaction is 0.693 over your rate constant called K. Or you can use ln 2 over K. Now, my recommendation is I will prefer you to use the 3 significant figures called 0.693 because that is the 3 SF of ln 2 if you press your calculator. And your syllabus actually wrote there 0.693 lah. So I think we follow their significant figures. If they wanted the 3SF to be used, then we use the 3SF version instead of pressing the calculator using ln 2 that has so many decimal places behind there. All right, and then the decimal so-called the significant figures will be larger than your syllabus version. Okay, but I've seen marking scheme accepted the ln 2 version as well, but we do not want to take the risk. All right, so my recommendation is use 0.693 divided by your K to get your half-life. Okay, so there are 2 ways question that can come out. Normally, the more straightforward is please go and find the half-life so that I know that it is a first order. Okay, so you want to draw construction line and then you find the mean average time called 6.9. Okay, now, so let's say we continue from here. Okay, knowing that in your constructions line, you found that the average half-life is 6.9. So this number here is 6.9. Are you able to calculate your rate constant now called K? Then yes. So therefore, your K is 0.693 divided by 6.9, which is your half-life. Now, this formula is only valid for first order reaction, which is in your syllabus. You must know this formula. Okay, now this formula is not applicable for the 0 and second order reaction. Okay, it's not applicable because they have their own half-life formula for 0 and second order, which depends on the concentration of the reactant. So we're not going to cover this in the Cambridge syllabus. Okay, now, so I have covered method number 3, which is using half-life, and I would like to go back to the question just now. Okay, over here. Yeah, all right. So this one here, all right, we started off with a curved line to show how 2-chloro-2-methylpropane decreases over time. And this one uses method number 1. I see a curved line. I know it's between a first or second order, but I don't know which is the correct answer. It's either A, you make the student do another graph, which is time consuming. Then you look at the pattern here. Then the student know it's first or second order. B, second option is you do half-life. Okay, you do half-life. So over here, okay, first we answer the question. Use the graph to determine the rate of reaction at 40 seconds. Okay, so at 40 seconds, okay, for the sake of answering this question, I need the ruler. Okay, come at 40. So let's just approximately gauge. Okay, we just want to know the way on how to go about. Now 40. So let's say 40 is here. Okay, which is this cross here. Okay, now this is 40. So, and then you want to know the rate at 40 seconds. So please draw a tangent at 40. So I'm going to draw it very long. Okay, now, so over here, maybe I take this point called 0 and 100. This is one of my coordinates. I want to calculate the tangent, right? And let's say the second intersection here is called, oh, sorry, this is 100. X and Y. And the second one is 0 and 0.0125. I just do an approximation. Okay, so at minute 40, all right, you can calculate the rate, which is the change in Y. Okay, negative 0.0125 divided by 100. So therefore, the rate equals to negative 1.25 times 10 to the power of negative 4. Okay, so this is the rate. Okay, so Y divided by X, which is mole per dm cube per seconds. The unit is given in the question paper. Okay, so I'm going to answer here. The rate is 1.25 times 10 to the power negative 4. Negative, positive, not very important now. All right, because we know a decrease. Decrease means negative. Now next, use the graph to show that the overall reaction is first order. Okay, this is actually making you to do method number 3. So I'm going to erase the rest of the line here. Okay, you want to draw constructions line, okay, in this curve. So let's just quickly gauge. I start from 0.02, I drop half. Okay, and I look here. So let's say the time taken is 30. Okay, so my first half-life here, okay, first half-life, T half is 30 seconds. Now, second half-life, 0.01, drop down here. Okay, so let's say I speculate this 60. So the second half-life is 60 minus 30, which is also 30 seconds. So if I can do a third one, which normally I try, provided there's enough space given in the graph. So let's say here, speculate out is approximately 90. Okay, so the third bubble here, okay, so I'm going to write third half-life is 90 minus 60, which is 30 seconds. So we can see that the successive half-life okay, successive half-life is keyword here, constant at 30 seconds. Hence, it is first order. with respect, WRT, you will see this in the marking scheme, with respect to your 2-chloro-2-methyl. I just copy the whole thing. Propane, like this. So this is to show, using method number 3, half-life, that is a first order reaction. Okay, now I'm going to add an additional question down there in red color pen, which I've already annotated. Calculate the rate constant for this equation and give the unit. Rate constant is your K. Okay, so do you know how to solve? Okay, we need to bring out the formula. Okay, so the formula just now is half-life only for first order reaction. Okay, only for first is 0.693 divided by K. Now, since my half-life is 30 seconds, the average one, hence I can calculate my rate constant is 0.0231. What is the unit? This is in seconds. So hence your unit is S minus 1. Okay, so we have so far done method 1, method 2, and method 3. Okay, yeah. So normally method 3 will come out because it's a fair amount of effort from the student and not taking too much time. All right. So if you come out here, I've already covered the first one. Okay. The second one and the third one over here. Okay. Yeah. Now, so for the other two, okay, table and a rate determining step, we will continue in the next video.